Good afternoon, ladies and gentlemen. Thank you for joining us for the Rotating Machine section webinar today, where it's entitled Vibration Measurement and Analysis of Electrical Rotating Machines. I'd like to introduce you to the chairman today. But firstly, I just want to read you the webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this presentation will be made available on the SAIEE YouTube channel, SAIEE TV. The recording will also be made available on the SAIEE website under the events drop-down menu in the section Past Events and Webinars. These pages are updated regularly, so ensure to check back as often as possible for new uploads and subscribe to our YouTube channel. A certificate of attendance will be issued a few weeks after this webinar once we have received the CPD validation number from EXA. I'd like to introduce you now to the chairman of the Rotating Machine section, Jabulani Bembe. Jabulani Bembe has completed his B.Eng and M.Eng in electrical engineering from the University of Johannesburg. He also completed the B.Tech degree from Vaal Triangle Technikon. He holds the government certificate of competency in electrical and mechanical engineering. He has more than 20 years experience working in electrical machinery repair and research industry. He currently works for the South African Power Utility Eskom as a researcher specializing in asset condition monitoring. He is a member of the Institute for Engineering Council of South Africa, EXA, and the South African Institute of Electrical Engineers, and Institute of Mechanical and Electrical Engineering Council for South Africa. He is currently serving as the chairman of the SAIEE Rotating Machine section and a member of Eskom Steering Committee for Rotating Machinery. I hand you over now to Mr. Bembe. Thank you.
Thanks, Mix, for that introduction. We're really looking forward to the discussion that we'll have today under the Rotating Machinery section for the SAIEE. And today we have a very interesting discussion that we'd like to share with you. And the discussion is based on the measurement and analysis, vibration measurement and analysis of electrical rotating machinery. And the presenter to do that for us, and who some time ago was my colleague, and his name is Dr. Gordon. He's currently a chief engineer at the Gauteng Department of Health. He previously worked at the Eskom as a senior engineer involved in nuclear engineering and condition monitoring. He is a part-time lecturer of electrical machines at UNISA Department of Electrical and Mining Engineering. Currently, he's interested in multi-physics, simulations of electrical machines, and MATLAB simulink optimization of fuel cell powered locomotives. Without further ado, we would like to give that opportunity now to Dr. Mark Gordon. Dr. Mark Gordon, the time is yours.
Good afternoon, colleagues. It's an honor and a privilege to be with you this afternoon. The intention is just to give the listeners some touches on vibration analysis and measurement on electrical machines. I did this quite a long time ago, in 2003, as part of my master's. But I just want to bring it onto the table so that you know, as engineers, we discuss these things, and that it shouldn't be something that's too remote from us. So, as the title is, vibration measurement and analysis on rotating electrical machines. As we go through the talk, you'll see the machines that are actually discussed. Okay, so the presentation looks at the multi-generator set, which is the experimental setup. We briefly look at the electrical circuit, and then we go straight into some defect frequencies, varying defect frequencies, the calculations and the analysis. And then we end with a look at something to do with the windings, looking at some of the electrical measurements done on the windings. Okay, this photo is basically the setup. So you have a single phase machine, a single phase capacitor start motor, connected via a shaft coupling to the alternator, which is basically the car alternator. And this little box is the switch box. And here you measure the voltage and the current, etc. for each of the machines. And also you have a little rheostat, so you can vary the excitation on the alternator. And in that way, you vary the load on the motor. Here we have the frequency analyzer, which is an expensive piece of equipment. Not many people can get their hands on it, but they are available in the industry. So this is what I use to measure the vibrations on the experimental setup. And as we go, we'll discuss the various aspects. So here we have a diagrammatic representation of what we have. We have the single phase motor, that's basically the drive for this machine. And then we have the alternator and we have a shaft coupling. So what's important when you're doing vibration analysis is the positioning, where you put your sensors, you know, and the naming, the nomenclature of how you do your measurements. Because when you do measurements, you need to, for example, we can call this the vertical direction. And here you see the vertical, the axial, and then the lateral. So this is important when you do vibration analysis, that you look, that your measurement protocol, you know, is always the same. So it's an important aspect of vibration analysis. Here we go back to the main and the control circuit for the setup. So here's basically the power supply to the single phase motor. And this is what I call the control circuit, which is basically the power supply to the ammeters and the voltmeters, etc. And also for the excitation of the generator, of the alternator, we have a little rectifier here. You can see here the output of the alternator is connected to a resistive load after rectification. So these are commonly available machines. A single phase capacitor start motor, you can get them quite cheaply, and also the alternator, also, you know, you can get the scrapyards, etc. But the main focus is that when we look at electrical machines, we shouldn't think that they're too remote and that only some have access to them. If you're innovative enough, you can put a test rig together and do measurements which mean something. So that's the intention, to get our engineers to think along these lines. Next, I just put a couple of slides together looking at things like the measurement parameters. You know, you're either measuring vibration displacement, velocity, or acceleration. You need to know what these different parameters mean, and you know, the whole aspect of actually getting an FFT, fast Fourier transform, let's call it a frequency spectrum, it's quite complicated, but I mean, the literature is full of it, so you can learn a little bit about actually measuring the vibration. And then also, depending on the class of machine, like these are small machines, so you'll find that we have used the VDI standard. This is the German standard. But depending on the class of machine, you get various vibration, let's call it thresholds. So if you're like 1 millimeter per second on a small machine, doesn't mean the same thing as 1 millimeter per second on a larger machine. So you need to look at the measurement standards. And then sensor placement, as we discussed briefly, you're either measuring vertically, axially, or horizontally. So you need to know about the sensor placement and also the type of sensor you're using. Are you using a piezo device? What type of device are you using? The measurement protocol is basically the system used to measure your vibrations. And then we have just included the frequency spectrum, time waveform analysis, which are two different things. The one is in the frequency domain and the one is in seconds in the time domain. And then also just put in a brief issue on phase analysis. So phase analysis is important if you have things like misalignment and unbalance. So you actually can pick up whether two positions on your machine are moving in sync or out of sync with each other. Okay, typical vibration faults, misalignment, unbalance, bearing defect frequencies, mechanical looseness. In this machine, because they are brushes, you get something called a brush pass frequency, which is typically twice the rotating speed of the shaft. Then you get the pole pass frequency, which, depending on the number of poles in your machine, you multiply that by the shaft speed. Yeah, I've just got an example of a ball bearing, and as we go on, we look at the bearing defect frequencies. So one should remember that bearing defect frequencies occur, and they're not always above the allowable limit. If you look at your vibration standards, you can usually judge whether your machine has bearing defects or not. And these are some of the parameters you use to calculate your bearing defect frequencies. What's important is to get the bearing number. On a lot of these machines, you have the bearing number on the bearing. So if you know the bearing number, you can get the bearing data, and immediately you can go straight into vibration analysis, and you can find what are your defect frequencies. So we look at the different bearing frequencies which can be calculated, and these are the formulas. And these are basically the standard formulas that you can get in the literature. And this is called the BSF is the ball spin frequency. BFI is the ball pass frequency of the inner race and the outer race, etc. And the theta there is just the contact angle. So using a bearing data, you can actually calculate these frequencies. And yeah, I've just put together some of the bearing defect frequencies which you can calculate in an Excel spreadsheet, for example, if you have bearing defects. And yeah, I've got the frequency spectrum and the time waveform. The frequency spectrum, you can see the x-axis, so to speak, is in hertz, and the y-axis is in millimeters per second. The graph below that is the time waveform analysis, which is important if you're doing careful analysis to find out whether you have an erratic behavior or not. So when I do vibration analysis, I look at both the frequency spectrum, looking for defect peaks, and the time waveform analysis, which is important, especially if you've got looseness and other erratic behavior in your machine. And here I've just calculated your frequencies. This is what they call sideband frequencies. So if you know your shaft speed, right, you can calculate your harmonics, and these sideband frequencies occur either at 1 times the frequency on either side of the shaft speed, or 2 times. So these are both bearing defect frequencies, and as I say in the literature, this is quite easy to do. Leaving the vibration analysis, I just looked at some of the winding data. Look, these are simple machines, relatively simple machines, and you see for the capacitor start motor, these are the measurements I did. I looked at the temperatures. and then look at the winding data, and then went back to the standards. The ISA standards are common. So, and in the ISA standards, you can always verify whether your winding data is above or below the minimum standards, for example, for your insulation resistance. So you can see all these windings were taken at 21 degrees C. So look, you can also use your winding data to look for faults. So if you have a fault, if your resistance is too high or too low, you can make some kind of estimation. And these are just by doing simple tests, using a mega for insulation resistance, and then using calibrated multimeter, maybe a fluke or something like that, to measure the winding resistances. And for the alternator, these are the winding resistance and the insulation resistances that I got. That's basically my talk, and I'm hoping that we can open up a discussion on vibration measurement and analysis, and those are some of my references. Thank you.
Thank you, Dr. Gordon. That was very interesting. We really appreciate your presentation and your time that you've allocated for us as a section for the Institute, and we really appreciate that gesture. Well, as you will know, colleagues, these two fields, your electrical and mechanical, are very intertwined fields, and at times as an engineer, you need to be able to understand all these things and be able to give a meaningful contribution when it comes to the analysis and condition monitoring of your machine. Well, let's do this now. Let's ask, try and answer your questions, and we would, as usual, just write your questions on the section on the right, and then we'll let Dr. Gordon answer that question. Thank you. See if we've got any questions from the audience. What is it that you'd like to know about the machines and how this presentation has helped you, or you want to help in the future? Wesley, do you see anybody on your side?
Currently, Jabulani, we're still waiting for the questions to come in. Okay. Maybe while we wait, I can ask Dr. Gordon a question.
Thank you.
It interests me, thanks. Dr. Gordon, you mentioned, about the different axes for measurements. If you're using, for example, an accelerometer. So on your tests and from your experience, how would this affect having those different axial measurements would affect the analysis as you've presented now?
Thank you, Prof. It's a wonderful question you've asked, and it's something I spent some time thinking about, because especially when you're involved in testing a mini machine, maybe similar type of machines, you have to have some kind of a naming protocol. For example, the measurements taken on the shaft end and the measurements taken on the non-shaft end. You typically will find that on the shaft end, because that's where the load is, you find that your vibration measurements are higher, right? You'll find that if there's some kind of an axial effect, you might find that you have axial vibration. All right. So that's why it's important when you do your measurements, you come up with a test procedure, and you say, okay, for example, on the drive end, on the non-drive end, this is the difference between, let's call it the millimeters per second, something like that, the vibration velocity. Then you start to get to know your machine. Mr. Bembe mentioned issues of electrical and mechanical being intertwined, and that's very true. You need to have a good understanding of what makes your machine work. Okay, from the electrical side, right? How the field how the field interaction gets your machine to rotate, for example, right? What's happening in the air gap, and as well what's happening with the load. So the measurement position helps you with that. You look at the vibrations, and then you start understanding, why does the machine behave like this? Is it because in the air gap we have these kind of effects? So that's why you've got a higher axial vibration, for example. So you have to have an integral knowledge. Fortunately, in my training, I was training traction motor, testing traction motors, right? Back-to-back testing of traction motors. So I spent a lot of time with the artisans and opening up the machine, seeing how they're repaired, for example, putting bearings in, etc. And then you get a good understanding of how the machine actually works. So when you do your vibration analysis, it becomes much easier to understand.
Thanks, Dr.
Okay,
Gordon.
thanks.
Jabu? Yeah.
Okay, thanks, Prof. Yak, thanks for that. Just I see also there's a question on the 2 MVA. The question is, how do the procedures differ for a single bearing alternator coupled to the flywheel of a diesel generator?
Yeah, that's, look at just in a locomotive or just in a generator as such.
Well, it doesn't say. Yeah.
Can you just repeat the question, sir?
It says, how do the procedures differ for a single bearing alternator coupled to the flywheel diesel generator?
Well, look, as I say, when you set up your test procedure, and you're looking for example, at the drive end of, let's say, the alternator, obviously you're gonna pick up what's happening in the diesel engine as well. So a good thing is to maybe test it decoupled from your diesel gen, and then when you test it coupled to your diesel gen, you'll notice the difference. So it's a good thing to be able to do no load and load testing. So which I was fortunately able to do. As I say, when I did my master's study, I was able, because the machines are small and you can handle them, I was able to separate the fault, so to speak. So you run the machine on no load, you run the machine with a decoupled load, you look at the vibration frequency, and then you put on the load, and then you see what happens. So when you do that kind of testing, you need to have a little bit of time to actually, besides understanding the machine, you need to note what will happen. For example, if you have like pistons, right, IC engines and stuff coming from your diesel engine, obviously those vibrations will be transferred through the shaft. So you need to look at to separate the issues. I think that's a good place to start.
Thank you, Doc. Les, Prof. Wesley, I think there's another question there.
Yeah, sure. Thanks, Shabu. Dr. Gordon, so there's a question from Derek McKinnon asking, how is variable frequency handled? So in the face of bearing mechanical resonance. So if you have resonance, how is that handled?
Well, look, thanks for the question. The important thing is to understand the mechanics, right? What you can do, if you're into multi-physics modeling, you can look at the structural aspect of your machine, right? So usually you can use something like unbalance as the driver, the driving frequency for your vibrations in the machine, right? So unbalance is just, if you can imagine a shaft running off center. So you put some value to that, and you use that as a structural input into your model, so that you can look at resonance, right? And obviously resonance is, you're going to be looking at the weight of the machine, you're going to be looking at the different rotating masses. So you come up with some kind of a structural model, and then you can relate that to the resonance of the machine. And then, you get these different tests, like where you impact the machine and you measure frequencies, right? So you impact the machine, like a bell ringing. You impact the machine and you see how it rings, at what frequency it rings. Then you use these things in your structural model, and then you look for resonance. But usually your machine will be able to tell you if you're running near resonance or not. The artisan that I trained under used to use a broomstick, right? Take a broomstick, put it on the bearing housing, and listen to the broomstick, all the ringing and stuff in the broomstick, and then you'd be able to tell you the fault in the machine. So it's like an archaic way of doing things, but the machine will tell you how it's behaving. I hope that question helps somebody.
Thank you. Thanks.
Just on my own, if I can ask Dr. Gordon, in terms of your unit at which you analyze the vibration analysis, at which you do your vibration analysis, the difference between between acceleration, velocity, and displacement, how does this difference impact in terms of your actual values? Because I know we've had some instances where you quite battle if, for example, the instrument measures in acceleration and you have to take it down to displacement, then you always have this discrepancy in terms of, because you're integrating and you're doing, there's a maths involved there. So how does that
Look, typically I mulled over this. I remember when I was doing my studies. Typically, you get tables either from the VDI or IEEE, etc. For the particular class of machine, you get tables, right? That obviously, if you're in a linear regime, because sometimes you get nonlinear vibrations, right? If you're in a linear regime, then some of the tables help you to corner your issues, right? For example, to change from acceleration to velocity. Your tables can actually help you. But it depends on the situation. But I usually think of F is equal to ma. And and I kind of relate the acceleration to the force, and I use that as a guideline, if that helps any. But
thanks,
the issue is, as I say, you get nonlinear effect. So what's important is to test your machine at particular conditions, right? Let's say 3/4 of full load or full load. Right, and look at how the machine runs maybe for a couple hours on full load, right? And then on another day, heat up the machine, run it at that same load, and look at what measurements you get. And then also look at the frequency analysis. Look at what frequency those measurements were taken. This is why it's important to understand both the measurement aspect and the analysis. Because analysis will tell you what your fault frequencies are. but you must know where those fault frequencies come from. And the only way you're going to know that is if you understand the machine.
Thanks, Doc. That's appreciated. Okay, let's see if we've got any other question. See, Derek has already been answered, so let's see if somebody else wants to know something about their machines. I think we have exhausted the questions, Prof. Dosami. I don't see anybody else asking a question unless we. Yes. Go ahead.
I see. We've exhausted. Maybe I can just answer the last question. Probably something out of interest, and yes, it might be a little bit of an academic question. Dr. Gordon, I've come across some literature before in practice where people are. There's this argument of discussion around use of wavelet transforms versus Fourier transforms. Have you, your experience, have you found anything useful coming out of wavelet transforms versus Fourier transform?
I must admit, I haven't really been following. I read a little bit on the wavelet transform, but I must admit I don't know too much about it. The Fourier, it depends on the machines that you have available, what techniques they use to analyze the signal, and also the processing time and things like that. But let's call it from my point of view, it depends on what software and what hardware you have available, But there's nothing getting away from the, let's call it the electromechanics of the system. I think that's very important because as I say, you can have all the sophisticated software, and it can do the analysis very fast or efficiently for you. But in vibration analysis, you need to have an understanding of the electromechanics. I hope that can help someone.
Thank you. Over to you, Jabu.
Okay, just another question. In terms of your electrical components, electrical data and the mechanical data, how did you make that link? Because I'm trying to find out if you've got this kind of operation and you do your electrical test and you find a certain figure. How do you? Is there a way that you can kind of superimpose the two and say if I have a vibration of this sort, this area, and I'm more likely to see a winding resistance of this much, or how do you marry the two?
That's a wonderful question. Thank you. The issue is that I believe a flux coil, right, can do a world of good for anybody who's really interested in tying the two together. The mechanical vibration aspect, as well as how the machine is operating. There are a lot of papers on, you can make your own flux coil, right? And they call that current signature analysis. So what one would typically do is get a flux coil, put it on the on the bearing housing, hopefully around your shaft, and also depending on how far your coil actually reaches, whether it goes around the air gap area or not. But that that you can do from trial and error. And once you have an idea of the current signature, then you can start talking to the vibration signature. And I think you're well on your way to actually diagnosing faults on the machine.
Okay, that's interesting. Thank you very much, Dr. Gordon, once again for availing yourself to share knowledge with us and our members at large. And we're looking forward to more presentations this type in the future that you can share with us. Wesley, I'm not sure if I've left anything, but just before I finish off. Yes. Anything you want to add, Doctor?
Joanne has just pulled up a question here, looking at
okay.
Can VSD control of traction motors have an impact on the gear wheel combination? I think
okay,
this is. I think. Yeah, yes, I think I'll go right back to my point on the current signature analysis, because when you have switching in your let's say in your electrical supply, that will affect your that can also have, because your switching will affect your electric field, basically your magnetic field, sorry, and because your switching affects how the magnetic field behaves in the air gap. If you use current signature analysis, you can really have a good idea of what signals to expect, even on your vibration side. Because what happens is you have pulsing in the machine, right? And if you have pulsing in the machine, and you can have those effects on the mechanical side as well. It's like banging, banging something. Let's call it like banging and rotating. So you can feel those impulses on the mechanical side as well. So I would suggest that you have a current signature analysis as well as a vibration analysis from your mechanical sensors, and you look at those two together. That's my humble submission.
Thank you, Dr. Cody. I think you can see that there's quite a range of questions that people are interested in, and we thank you very much for responding to that. However, you would know if any questions comes to your mind and you cannot be able to raise it now, you're more than welcome to put it onto our website and then send that question to the rotating machinery section, and Dr. Gordon will do well to come back to you and answer that question. Thank you very much.
Thank you so much.
Yeah, just as a note of closing, we just want to thank you, Dr. Gordon. We want to thank the attendees as well for joining us, and we're looking forward to seeing you again next time. We just want to I want to whet your appetite. We have another webinar coming up this month. Look out for the experience that we want to share with one of us. That is Nico Smith, that used to work for Eskom some time ago, is now in New Zealand, and he's got something to share with us because he's still doing something that he used to do once at Eskom. But it would be nice to know what is happening in that part of the world as compared to what we do in South Africa. So look out for that webinar and make sure that you join us as well. I think from my side, that would be all. I don't know, Wesley, if you've got anything that you need to mention.
Nothing from my side. Thanks, Jabu.
Okay. Okay. Thank you very much. See you next time.
Thank you.
Thanks.